surface area of solids fixed onto flat surfaces, the subtraction method. Hello everyone. Today, we are going to dive into a very interesting subsection of geometry. We will be exploring a specific scenario where we deal with composite solids. That is, situations where one solid object is attached or fixed onto the flat surface of another. To help you visualize this, think of a common decorative item, such as a hemispherical ornament fixed right onto the top of a cubic block. Now, as we move through this lesson, you'll see that our primary challenge isn't just looking at the two shapes separately, but determining the total surface area of the resulting combined object. We need to figure out exactly how much surface is still visible once they are joined together. Understanding the concept, the hidden surface. Now that we've introduced the topic of solids fixed onto flat surfaces, let's dive into the core concept that will guide our entire calculation. This is what I call understanding the hidden surface. Think about it this way. When we attach one solid to another, the specific area where those two shapes meet is no longer exposed to the outside world. It's tucked away inside the structure. In mathematics, when we talk about total surface area, or TSA, we are strictly interested in the surfaces that are visible and accessible from the exterior. To make this even clearer, imagine you were holding this combined object and you wanted to paint it. If you were to dip the object in paint, you wouldn't be able to reach or paint the area where the two shapes are glued together, right? That part is hidden from your brush. Therefore, the most important rule to remember for our upcoming steps is this. This contact area, the part where the shapes touch, must be excluded from our final calculation. We only care about what remains on the outside. The step-by-step methodology. Now that we understand the concept of the hidden surface from our previous slide, let's move on to the practical application. I want to give you a clear, logical roadmap so you can approach any problem of this type with confidence. We call this the step-by-step methodology. First, let's look at step 1. You start by calculating the total surface area of the base solid. Imagine the larger object, like the cube we mentioned earlier, is sitting there all by itself, completely untouched. You find its total surface area as if nothing were ever attached to it. Next, in step 2, we need to identify and calculate the contact area. This is the most crucial part. Look closely at the base of the solid that is being attached. What shape is it? If we are attaching a hemisphere, the part touching the cube is a circle. We need to find the area of that specific circle, which is pi r squared. This is the area that is about to become hidden from the outside. Moving to step 3, we calculate the curved surface area, or CSA, of the attached solid. Remember, because the base of this attached shape is now glued down, it is no longer part of the exterior. Therefore, we only care about the part of the shape that is still visible, its curved exterior. Finally, in step 4, we bring everything together using what we call the subtraction method. This is the formula you'll want to memorize. To find the total surface area of the combined solid, you take the total surface area of the base solid, subtract the area of the contact surface, and then add the curved surface area of the attached solid. In the next slide, we are going to put this exact formula into practice using a real-world example of a decorative paperweight. Real-world example, a decorative paperweight. Now that we understand the theory behind the subtraction method, let's put it into practice with a real-world example. Imagine we are designing a decorative paperweight. In this scenario, we have a hemisphere with a radius of r, and it is fixed directly onto the center of the top face of a cube that has an edge length of a. Our goal is to find the total surface area of this new, combined object. Let's walk through the solution step by step, following the methodology we just discussed. First, step 1, we need to find the total surface area of our base solid, which is the cube. If we treat the cube as if it were completely alone, the total surface area of a cube with edge is 6 squared. Next, step 2, we must identify the area of the contact surface. Remember, this is the part that is now hidden from the outside. Since the hemisphere is sitting on the cube, the contact area is the circular base of that hemisphere. Therefore, the area of contact is pi r squared. Step 3. Now, we calculate the curved surface area of the attached solid. Since the flat base of the hemisphere is glued down and no longer visible, we only care about its curved exterior. The curved surface area of a hemisphere is 2 pi r squared. Finally, step 4. We apply the subtraction method formula that we learned in the previous slide. To find the total surface area of the paperweight, we take the total surface area of the cube, subtract the area of the contact surface, and then add the curved surface area of the hemisphere. When we plug in our values, the equation looks like this. The total surface area equals 6 squared minus pi r squared plus 2 pi r squared. Now, let's move to the next slide to see how we can simplify this expression into a final, clean formula. Simplify the expression. Now that we have set up our full expression from the previous step, we reach our final step, step 5, which is to simplify the expression. If you look at the terms we have negative pi r squared plus 2 pi r squared. Since these are like terms, both involving pi r squared, we can combine them. When you subtract 1 pi r squared from 2 pi r squared, you are left with just a single pi r squared. Therefore, our final simplified formula for the total surface area of the paperweight is 6 squared plus pi r squared. This elegant little formula tells us that the total area is essentially the surface of the cube, plus the extra area added by the dome of the hemisphere. Key takeaways. Now that we have worked through our paperweight example and simplified our final expression, let's pause and recap the most important key takeaways from this lesson to ensure you have a solid grasp of the concept. First, always keep the principle of exposed surfaces only in mind. When you are calculating the total surface area of a combined object, you must only account for the surfaces that are on the exterior. If a surface is tucked away inside the object where two shapes meet, it is no longer part of the total surface area. Second, let's revisit the logic behind the subtraction method we used in our calculation. We subtract the contact area specifically because that part of the base solid is now covered by the attached solid. It has been moved from the exterior to the interior, so it must be removed from our total. Finally, a very important distinction to make is the difference between curved surface area and total surface area. When you are adding the attached solid to your calculation, always use its curved surface area, or CSA. You should not use its total surface area, because the base of that attached solid is hidden against the other object. Understanding these 3 points will help you avoid the common pitfalls we are about to discuss in our next slide. Common mistakes to avoid. Now, before we wrap up today's lesson, I want to touch on some common pitfalls. Even if you understand the subtraction method we just practiced with the paperweight, it is very easy to make a mistake during an exam if you aren't careful. First, please avoid the temptation of simply adding the individual total surface areas of the two shapes together. You might see a cube and a hemisphere and think, I'll just add their TSAs. But remember what we discussed in slide 2 about the hidden surface. If you add the full TSA of the cube to the full TSA of the hemisphere, you are actually counting that circular contact area twice, once as part of the cube and once as part of the hemisphere. In reality, that area is hidden and shouldn't be counted at all. Second, watch out for the mistake of forgetting to subtract. It is a common slip-up to calculate the curved surface area of the attached solid and add it to the base solid, but then completely forget to subtract the area of the base that is now covered up. Always remind yourself, if it's covered, it's gone from our total. Finally, a very simple but frequent error is the confusion between radius and diameter. When you are working with our formulas, such as pi r squared or 2 pi r squared, ensure you are using the radius, or if a problem provides you with the diameter instead, make sure you divide it by 2 before you start your calculations. Keep these points in mind, and you'll be able to approach these combined solids with much greater confidence.